We now have a session on multi-display and cluster API. And I'd like to welcome to the stage Andre and Roberto, who will tell us a little more about that.
Hi, everyone. I am Andre. I'm a software engineer in Core Framework team. I work on multi-display and activity lifecycle. Today, in our session, we'll have two parts. First, I will tell you a bit about multi-display, and I will be followed by Roberto, who will tell you a bit more about cluster and cluster APIs. So for multi-display, we'll start with an overview of the topic, and then go through different screens in a car and see what specifics they have and what kind of configurations and what kind of modifications you might need to do for your setup. So first of all, when we are talking about multi-display, we mean support for showing activities and windows on screens that are different from the primary screen. And this is the central topic of what we've been working on in Android over the last couple of years, because Android was primarily written with a single screen and full screen applications in mind. And we had to change a lot of assumptions in order to deliver all these new features. There are multiple different types of displays in a car. First of all, they can be physical or virtual or embedded in the form of a software display in another screen. Screen can be driver-oriented and passenger-oriented. And a driver-oriented screen will probably have more restrictions applied to it. For example, it should not show not optimized content when the vehicle is moving at speed. The screens can present different kinds of applications, and they can be operated with different forms of input. For example, some of the screens will be touch operated, and others will have hardware knobs to control them. So here are some ideas for screens in the car. As you can see, there are lots of them. And some of these screens can be fully powered by Android, while others can get content, visual or text content from Android and embed and present it in a display powered by a different car operating system, like instrument cluster display, for example. And a number of users can be interacting with the car with different screens in the car at the same time. And this is something that we paid a lot of attention to when we were working in Q. And here are the key elements that I'll be using when talking about multi-display. So we usually distinguish activities, forms of input, and software keyboard, and also various types of system decorations, like status bar and notifications on top, home screen activity, navigation bar on the bottom, maybe wallpaper behind it. Let's take a look at the history of how multi-display evolved over the course of a couple of years. So the modern history of multi-display starts with O, when we first introduced the ability to show activities on non-primary screens. And this actually involved a significant refactoring in activity and window manager. We needed to restructure the entire organization of classes and nodes to be able to achieve this. And also we added a new API to allow both system and applications to launch activities on secondary screens. In OMR1, we first introduced the modern iteration of Activity View, which is a container that allows you to embed an activity into another activity. In P, we made a lot of under-the-hood improvements, both in Window Manager and in Activity View specifically. And then Q is by far the biggest release for multi-display. We added a lot of stuff there. We added stable display identifiers. We provided you a way to automatically route input in your system. We added a number of system UI components, improved software keyboard support, and so on. And we still have a lot of work to do in the future. I will talk a bit more about this in the following slides. So it is important to understand where it all began in O. This is the graph of nodes used by Activity and Window Manager as an internal hierarchy. So at the root of the graph, you see a device. It has displays, and then each display has activities organized in tasks. And this hierarchy is very important. It allows us to operate not only on individual activities, but on entire nodes and subtrees of this hierarchy using a single operation. It also gives us notion about the Z order. The Z order means usually represents what user last interacted with. So in this hierarchy, the activities that are to the left are higher and are covering the activities that are to the right. And also we added this API. This is how it looks like if you want to launch an activity on a specific display. In Q, we covered almost 200 different feature requests and bugs, and we fixed a great number of limitations and assumptions of a single display that were baked into the system since its beginning. We improved software keyboard experience a lot. We added support for concurrent user input. We added support for more than 2 physical displays and ability to statically identify screens and much more. This meant that we had to change a lot of different system components, starting from lower levels like hardware composer and Surface Flinger, and going up to system UI and even client-side framework. So we recommend you to stay as close as possible to vanilla implementation of Android. And we try to help you with, in that by providing different configuration options that you can use to customize your experience instead of modifying the framework code itself. Because rebasing this stuff will not be fun, and we are continuing our work. And one of the examples in Android Q, the entire activity management code base was moved to a different location. So if you had patches there, well, it's always better to work with us on future feature requests for future Android releases and try to bake in the capabilities you need into the platform beforehand. Now let's go through different in-car scenarios. And we'll start with displays that are fully powered by Android and those that are usually meant to be used with touch. So in our car example, this would be those screens. Central driver and passenger screens in the front, and also rear screens in the back. So first and foremost, in up to Android version P, the system only supported 2 physical displays in hardware composer and display manager levels. And they were identified as a built-in screen and as an HDMI external screen. So starting with the upcoming release, Android supports more than 2, actually arbitrary number of hardware screens, and both in display manager and Surface Flinger levels. And Activity Manager and Window Manager already supported arbitrary number of screens before Q. And in addition to display identifiers, dynamic display identifiers that were available before, we now have static display identifiers. It's a very powerful tool. It allows you to configure your system functionality on per display basis without actually modifying the framework code itself. And we provided a way to automatically associate display and input. So let's start with identifiers. In a lot of cases, you need some way to uniquely and statically identify a screen. And regular integer display IDs that are available from display class are actually not stable. So the same display can get a different display ID across reboots. And the reason is because these IDs are assigned based on the order in which displays come up during the boot time. So if they come up for some reason in a different order, they can have different displays. And in Q, we added 2 new ways to uniquely and statically identify screens. So first of all, the existing value, the existing field in display info class called unique ID was updated. it now contains much more information about the type of the screen and also information that identifies a specific type of the screen. And it also is guaranteed to be stable across reboots and even across hot plugs. If you need to plug in and then remove and plug in again a display, it will get the same unique ID. And you can check the output of this shell command to see how they look like for different screens in your setup. The second way is dedicated class called DisplayAddress. It's also part of DisplayInfo. And in Q, we added two different types of display address. One for physical and for network or displays connected via network. So for physical display, it actually contains accessory methods to easily get port information and EDID information. For network, it contains network address. Keep in mind that this capability comes with hardware abstraction layer 2.3. If you have an older HAL, then you will get a simplified information both for unique ID and display address. Stable IDs actually allow us to do a lot of new things. So let's start with display input association. Using an IDC file, input device configuration file, you can now provide mapping between inputs or touch panels in your device and displays. So in this case, we have displays connected to port 0 and 1, and we have some touch panels connected to some USB ports. And the input framework will take care of everything else starting from here. So it will route all the input events automatically. It will assign the correct display IDs, and it will send them only to the displays where you need them to be. And by the way, this is also possible to use for virtual displays as well. But instead of the port information, you will provide unique ID. Another example where you can use static display identifiers is to configure different windowing options. So they are usually set in display window settings class in Window Manager package. It allows you to configure support for system decorations and IME. It can allow you to set force size, density, and scaling mode, set some fixed user rotation, default windowing mode, and so on. And you have two different ways to change these settings. You can either use the Window Manager APIs to change them at runtime, or you can use an XML file. So this is one of the examples of an XML file. And in most cases, this is the preferred way of doing this, because most of these settings are actually read and initialized once per boot at boot time. So you need them to be ready before the Window Manager is loaded. In this case, we are using a config identifier equaling 1, meaning that we want to use display ports as identification information for displays. Another option, you could set 0 there instead, and you would use unique ID. And for display connected to port 1, 2, 3, 4, 5, we enable system decorations, and we say that we want to show IME there. Keep in mind, though, that this settings file is persisted in data directory, so it may be wiped via factory reset or data wipe. And the reason is it also contains some of the settings that a user can potentially change during the lifetime of a device. So you need to make sure that this file is available and maybe contains the default values in it before the Window Manager boots. Talking about system decorations, each display can now be configured to show them, and these are the system decorations that we support on secondary screens. So primary screen supports all of them and more. Secondary screens in Q can display wallpaper, launcher, navigation bar, and IME. So wallpaper will automatically adjust to the screen size, and by default, the same wallpaper as on the primary screen will be used on secondary screens, but you can customize your system to display different wallpapers. Navigation bar, by default, will show only the back and home keys, but you can customize it. Like in this case, it shows an array of different buttons as shortcuts to different actions in the system. And if your system UI has more decorations panels, like for example, in this case, we have status bar showing up here that unfortunately we don't fully support yet. You can add more windows yourself. Just flag them with this flag is screen decoration. This will let Window Manager know that this is part of the system UI, and it provides insets for the applications that run on the screen. So for example, in this case, we have navigation bar provided by the system on the bottom, and we have a status bar provided by you on top. And then when the launcher activity is displayed, it is automatically positioned and resized between those bars. Speaking of launchers, we added a new category to intent filter to allow you to provide a dedicated launcher activity or home screen activity for secondary screens. Instances of this activity will be used on all screens that have system decorations enabled. And this activity must not have a launch mode that limits it to a single instance, like single instance or single task. And it is expected to be able to adapt to different screen sizes in your setup. You can use the same activity for all screens, or you can use one activity for your primary screen and a different activity for all other screens. Software keyboard was also updated. It can now be shown on secondary screens, which was not possible before Q. And if display is configured to show system decoration and some application requests input there, then the keyboard will show up there. If the display does not support system decorations, but some app requests input, then the keyboard will automatically fall back to the default screen. So now we've covered some common elements and configuration options that apply to all screens. Let's take a look at what's special about driver-oriented screens. So in our example, this would be this particular one. And because it is meant to be used by driver, it actually has more restrictions applied to it. So driving safety is very important, and driver safety restrictions will be applied to will need to be applied to driver screens. So this means that only certain set of whitelisted apps can be allowed on these screens while driving, and other screens that are meant to be used by passengers, for example, screens on the rear seats, they should not be restricted usually. So you can mark them by using the car service restriction mapping resources. Also, unfortunately, we don't have information about where a virtual display is nested or embedded on a different physical display. So this means that we need to apply driving restrictions for all the virtual displays in the system. And the reason we didn't fix this gap in Q is because we are working on a better, more targeted solution for embedding content in future Android releases. So an example of activity view, it's a container. It's actually a view that allows you to launch different activities inside your, for example, home activity in this case. And it works by creating a virtual display, and then it pipes all the input that comes in this region to the activities that run inside. So as I mentioned, it actually has security restrictions applied on all displays. So this means that it's better only to show it on the front scenes right now, because if you have passengers in the rear seats operating with activity views, then they will also get driver restrictions when they don't actually need those. In Q, activity view was optimized and polished. So now it's automatically faster, and it responds to touch quicker than before. It still uses virtual display, but I wouldn't recommend you to rely on this fact because it may change in the future. The only stable part of activity view is the concept of and its API that allows you to embed an activity in some container where you need and put it where you need to place it. Moving on to screens that are meant to be used by all passengers in the cars. So in our car example, let's talk about the the passenger screen in the front and also rear seat entertainment. So first of all, up to Android P, it had restrictions about what types of activities can be actually put on different screens. For example, an activity that is declared to be non-resizable or not support multi-window would also not be put on a secondary screen, and it will automatically fall back to the default screen in this case. In Q, more types of activities are allowed on more screens because we now apply certain compatibility modes to allow more different apps run on secondary screens. Let's talk a bit about how activity launch is resolved in a multi-screen scenario. So let's say that you want to start an activity from a home screen. And if it's a new instance of an activity that is being created, then it will be launched on the same screen as the caller. So for example, in this case, if I launch Maps activity from the screen on the right, it will automatically show up there on the right. And it will be shown on top of home screen and will cover it. If I go back to home screen and launch Maps activity again, the system will find the existing instance on the same display and it will just bring it to front. So it knows where activity was before. So we'll try to bring it up there again. So what if you need to launch activity on a different display? Like you wanted to move it to the left screen. In this case, you can use the Activity Options API and provide the target screen. And once again, first of all, the system will try to find an existing instance of activity. So for example, if you had Maps on the left screen and you want to launch it on the right screen, it will move it there. It will remove the Maps activity from the left screen. And if you continue doing that, it will just continue moving the existing instance of activity. So what if you want to actually use multiple instances of the same app? The Android API allows you to do that, but you will need to customize the app itself. In some cases, it makes more sense because you want to allow multiple users to operate with the same activity at the same time. For example, the kids may be playing the same game on the rear seats. And an application can declare support for it by using this launch mode. For example, they can use document launch mode always. And also, the thing that launches the activity, most often the home screen, it can add flags, multiple task, and new task to request a new instance of activity is possible from the app. And if the app supports it, then it will create a new one. Keep in mind that most third-party applications actually don't support this, and they will only have a single instance of activity. But you can build this into your applications provided by you in your system image. So let's take a look why adapting an application is a challenging task for this kind of setup. So let's take YouTube as an example. First of all, if you have two passengers that want to launch YouTube at the same time, when they try to launch a YouTube application, it can find an existing instance of a different display and take it away from a different passenger. And the reason is YouTube simply does not support this. And you don't really want to steal this activity from a different person. It will be very disruptive for that. Next, even if YouTube supported this, in most cases, users would likely want to use different user accounts. They would like to show videos, to watch videos that they like to watch and log in with their accounts. And this, again, requires separation of processes and separation of data. So the actual answer to this question is you need to support multiple concurrent users at the same time. This is something that we don't have in Android yet, and we're still working on this. Next is audio routing. So the audio from this application needs to be routed to the speaker set that corresponds to the seat where it's being watched. And the system does not do this automatically. An adapted app can do that by using this special media's audio zone, multi-zone APIs. But most of the third-party apps would not be able to do that. And also, app notifications that an application posts, they need to be shown on a particular screen. But sometimes it can be shown from a background service or some other entity, and Android would not know where to show them. So in Q, all notifications are still shown on the primary screen. And you probably don't want a notification from YouTube application that is running on the rear seat to be shown on the central driver display. And last but not least is activity launch. So some of the activity launches actually originate from another activity, like from home activity, and we know where it comes from. But others can be coming from background services, from content providers, or from other components that are not tied visually to any particular screen. So Android will not know where to put this activity. Once again, by default, it will use the screen that was last focused or the screen that was last interacted with, but this may not be something that you want in your particular setup. So what you can do if you actually want to prevent some rogue apps from accidentally or intentionally putting applications on driver screens and disrupting the driving experience. So first of all, by default, we recommend you to mark all the front seats, or at least the driver seats, as private. This will mean that only the system and the applications that are already running on that screen will be able to launch activities and put windows there. Other callers that have internal system window permission will be able to do it as well. But other third-party apps in the system will not see this display. And even if they try to guess the display ID, they will not be allowed to put any content there. In some cases, you may want to always show specific activities on specific screens. And in other cases, you may want to conditionally reroute an activity launch to a different screen. And launch params controller class is actually a very powerful tool that allows you doing both. So the way it works, it intercepts all activity launches in the system and gives you a callback, allowing you to modify the activity launch and modify the parameters. So for example, you can change the target display ID. This is a very useful tool because, for example, you can enforce that certain applications will only be shown on a driver screen and only there and will never be moved away to a different screen. Or you can make sure that games will never show up randomly on the driver screen if something bad goes in the application itself. Next topic is multi-focus and multi-session IME. So this is important when you want to separate user flows and allow users to work independently in different apps and do not disrupt each other. Specifically for automotive, we added feature to allow multiple focused windows in the system, and we added support for multiple IMEs at the same time. The way it works is that each display that has a focused text field will get its own instance of IME, and it will get a single focused window. Once again, the IME will only be shown where on displays that have system decorations enabled in display window settings class that I was talking before. If a display does not have display window settings flag that enables IME, then the IME will automatically fall back to the default screen. To try multi-session IME, first of all, you need to enable per display focus. It will not work without this flag. Then enable IME support in window settings, and make, install, and select multi-client input method as the primary input method. You can only use either this multi-session IME or regular IME. Those are two services that can be used only one at the same time. So you need to select which one makes more sense for your particular case. For example, if you want to allow multiple passengers and driver interact with different screens in your system, then multi-session AME makes the most sense. If there is only driver interacting with one or two screens, maybe a single session AME makes more sense. And multi-session IME service has a different API than the regular IME. So it's not compatible with existing keyboards and with third-party keyboards. But we have provided sample in Android sources, and you can implement the multi-session keyboard that suits your needs best. So taking a look at rear-seated entertainment, we actually covered a lot. So input is now automatically associated with correct displays, and user interactions are much better separated, and navigating within an app will not disrupt other users working with the system. But there are still a lot of areas that are missing. For example, audio will not automatically be routed, and in a lot of cases, you need to support multiple instances of the same app. So you need to keep that in mind while working on your system. Let's take a look at the instrument cluster display. In our example, this one here on the left. There are a few caveats about this. So first of all, what we learned is that using a physical display might be easier than using a virtual, because that way you don't need to implement your own HAL. And you also need to always restrict access to this display as much as possible to prevent random apps from appearing there. So flag private makes a lot of sense. And you probably won't be interacting with this display with touch, and you don't need IME or navigation bar there. So you can disable all these features as well. Let's take a look at an example of the configuration of a car and describe all the configuration options that you can use to support it. Let's say that our car has a central driver display, an instrument cluster display that provides some information from Android, and two rear seat screens. So first of all, each of these screens will need to be connected to the correct port, so that you can provide a single configuration file for the model of the car, and then it will work everywhere. In our case, let's say that the main display is connected to port 1, port 0, cluster is at port 1, and rear seats are ports 2 and 3. So input mapping file will basically look like this. So we are saying that displays are connected to some arbitrary USB ports here, and we don't configure any touch for cluster display because we don't need it there. Next, we need to set a number of framework overlay configs. So the first one says that by default, these displays should be configured as private in your system. In this case, we are saying that display with port 1 should be set as the private, the cluster display. Next, we select the launcher component that will be used on secondary screens. And we say that the system always needs to use this particular launcher component, and so that users will not be able to switch this home activity to a different one that they can sideload. And the last one says that we want to use multi-focus, one focused window per display in our system. After you enable multi-focus, you can start using multi-session IME. So we have a sample at this directory, and these are the steps you need to take to build and install and set it as the default one. After that, when you boot the device, multiple instances of IMEs should show up on different screens. And let's configure some windowing settings. So once again, we are saying in the first line that identifier 1 means that we are going to use display ports as identifying information for our screens. We don't need to provide any specific configurations for primary screens because it already has all the system UI and other components enabled by default. For cluster screen, let's say that we want to set a force density of 160, and we identify it by port 1. And for rear screens, we probably want to enable system decorations and IME, and also set some forward density. And you can repeat the same action for the last rear seat screen. So that's actually all of the steps that you need to do. Let's take a recap of what we covered today. So in Q, we added a number of features. Stable display identifiers and input rounding are the most fundamental and the most crucial among them. But we also added a lot of other features, and we worked a lot to separate user flows on different screens. There is a number of small to medium to large fixes that we didn't even cover today because there are just too many of them. And Q overall is a very big improvement in terms of multi-display over P. But there is still a lot of work to do. So supporting multiple users is a very, very challenging topic. And the reason is that because each individual system server component needs to be adapted to be aware of it. So for example, in Q, we added some support for multiple instances in system UI. And we can now show things like a navigation bar and wallpapers and launcher in multiple places at the same time. But there are a lot more work to do, and each individual piece of the system needs to be adapted to be aware and to take action based on the knowledge of multiple users running at the same time. Display power state and sensor data are still global in Q. And this means that if you want to set brightness automatically for your screen, unfortunately, it will set it only for one display or for all displays at the same time. Per display vsync and automatic audio routing are also the topics that we are aware of, that we are working on, and they are also important to achieve general app compatibility. And with that, I would like to hand it to Roberto to talk more about cluster APIs.
Hello. Hi, my name is Roberto Perez. I'm a tech lead at the developer story team, and I'm going to be talking about cluster integration and navigation APIs. So I'm going to start by stating what we are trying to achieve. That is a seamless integration of the experience of the cluster, the display that is behind the steering wheel, with the rest of the Android system. The APIs that I'm going to be talking about are mostly about coordinating what is being displayed there, rather than the actual setup of the display that Andre has already reviewed. So what are some of the use cases? Some of the ideas is to present Android render content. It could be, for instance, media or communications, like an incoming call, or it could be navigation, like what we have in the example. The idea is to coordinate between multiple applications. Like it could be that at the given time in the system, there is more than one navigation application that the user can choose from. So we want to coordinate which one is being displayed there. And to present navigation driving directions, like turn-by-turn guidance. We want to make sure that the navigation that is being displayed and the driver directions are coming from the same source, and they are not distracting the driver. We are not covering here like the safety critical portions of the cluster. As Andre mentioned before, things like the gear, the speed of the car might be better be managed by the unit that is rendering the display. And I'm not going to cover the details of how to set up the cluster display because we have already reviewed that. So this is a map that I'm going to use to go over each of the parts, and I'm going to review each one individually, starting from how the cluster is being set up and discovered. Everything starts from car service that starts as soon as the system boots, and one of the first things it's going to do is trying to find a class service implementation. Class service is just regular Android service that it has to extend from instrument cluster rendering service, which is the class we provide as part of the car library. The implementation of the cluster service is very straightforward. It's just extending this class. It's going to provide a set of callbacks. I'm going to review each of them individually. And the way the car service is going to discover this implementation is by a configuration file that you can modify with an overlay. So this string is going to point to the package name and class name of your own implementation of the cluster service. The manifest of that service has to have a few permissions. The service is going to run as a singleton, and the user 0 needs to be able to interact with other users in order to launch the UI on the current user that is logged in. And it has to have this car instrument cluster control in order to launch its own experience, its own UI on the display using the superclass. The service itself has to have this bind instrument cluster renderer service. This is a system permission. The goal is to prevent third-party apps from stealing access to the cluster. So only your own service is going to be able to be bound from car service. And once you have configured the discovery, your service is started, it's time to set up your display. Here there's a couple of options. On AOSP, the reference implementation uses a virtual display that transmits the video over regular network on H.264. This is only good for development. We are not recommending this for production. This is what you can find implemented both in AOSP and in the emulator to display the content of our fake cluster. On a production environment, we recommend using a physical display, sending over that display just the content of Android that you want to have on the cluster. And the rest of the information, like gear and speed and all the other information, just being rendered by that unit itself. In that second case, you can use the stable identifiers that Andre presented before to uniquely identify that display. You will have to also set up the rectangle that is going to be considered unobscured. This is the area where maps or the activity that is going to be displayed there is going to known to be able to display its own content. The content is going to bleed on the insets outside of that area, but this way the activity is going to know where to render important information. With all these details, like the display ID of the display that you have identified and the unobscure bounds, we can pass that information using activity options and the cluster activity state to the superclass, the instrument cluster rendering service. So these two methods are provided by the base class that I mentioned before. So we cover how car service finds your implementation of the cluster service. And now we're going to talk about the content that you want to display. So this could be your own regular activity. It's going to be launched by your cluster service implementation on Create. In the AOSP, what we have is one activity with multiple fragments. One of each shows a different experience, like a media facet, incoming calls, navigation. You can totally do this. Another option is that you just launch one full screen activity, like for instance maps, and you can do that by just using the start activity with the activity options that we saw before. In order to implement the experience, you will use regular Android APIs, media controller and media browse for media, the telephony manager for incoming calls. If you want to show, for instance, the state of the HVAC or the state of the windows, you can use the car property manager to surface that information. And you can check the reference implementation that we have. Is on the link on the screen. You're going to get these slides later, so definitely check that implementation. If you decide to show a maps activity on boot as a free navigation experience, you need to be aware that there may be more than one that you can present on the car at the given time. So you need to decide whether it's going to be something the user selects, like you provide a setup step where the user picks which app they want to use. It could be that it's hard-coded for each particular car, so you have a configuration file that defines that. You can dynamically check what is the navigation app the user used the last time and just launch that. In any case, once you decide to launch a navigation activity, you can use the base class method start navigation activity and pass the package name and class name of that activity. Once does launch, you need to be also aware that you need to relaunch it every time that navigation focus is released. I'm going to talk a little bit more about that in a second. So in our reference implementation, the way we select which navigation app to show is based on a configuration file. And here you can see how this can be modified using an overlay. Within our overlay, we're pointing to Google Maps. So the next thing I want to talk about is application focus. As I mentioned before, there could be more than one application that could request to be displayed in the cluster at a given time. In order to make sure that we only show one of them and that is consistent with the turn-by-turn guidance, we are providing an app focus manager that the applications can use to request focus. The system is always going to grant it and is going to revoke it from anybody else that has focus at that time. The instrument cluster rendering service is going to automatically use that to decide to launch that activity in the cluster. So on create of the service, you're going to launch your default experience, whichever it is. It could be Maps itself on free navigation. When a navigation application requests focus, like let's say that Maps or Waze decides to request navigation focus, you're going to get a callback saying on navigation component launched. And the instrument cluster rendering service is going to automatically launch the navigation experience of that app in the cluster. It's going to use the activity options you passed before during the setup step. It's going to launch that activity and it's going to notify the service. Once navigation is done, when the user has arrived to the destination, the application is going to release focus. The instrument cluster rendering service is going to notify the cluster service, and that's going to be the time to relaunch the default experience. So for instance, if you were showing the playing song and driving directions started and then they finished, you will relaunch that media experience again to bring the user back to the default. The way the instrument cluster rendering service identifies what to launch in the cluster is by checking the category navigation on, like it's going to look for an activity in the package that requested focus, and it's going to look for an activity with the category navigation, and that's going to be the one that is going to be launched. If you don't want instrument cluster rendering service automatically launching anything in the cluster, you can easily deactivate this by not providing an activity options to the instrument cluster. Then the last thing I want to review is turn-by-turn guidance. This is related to focus. Navigation applications can send their turn-by-turn directions by using the car navigation state manager. They can only do it when they have navigation focus. We don't want one app showing the map with the route and another map giving the turn-by-turn guidance. So that's why these two managers are coordinated. The content of this information can be displayed in many different places. We crafted this API so you can decide where to show and what to show in each place depending on your own model. In order to receive these events, you will implement, you need to create a navigation renderer, and you pass that to the instrument cluster rendering service by overriding the get navigation renderer method. This class has two methods. One is the navigation properties, where you can specify the rate of updates that your cluster requires, whether your service is able to render images or just text. And the most important method is the onNavigationStateChanged that receives a bundle with the actual information of the turn-by-turn guidance. In order to decode that bundle, you're going to use the Android X card cluster library. Here's an example on how to do it. Basically, you take the bundle, you extract the navigation information from it, and you pass it to the navigation state from parcelable method. That's going to give you an instance of navigation state. The navigation state object contains a lot of information. I'm not going to go over each of the fields. There's a lot of small classes and methods, but basically all the information that I mentioned before about maneuvers and lanes is encoded here. You can check the Javadoc public documentation on the developer side. So once you have this information, it's time to render it. And there are a couple of options. You can render it on the same activity that we saw before, the cluster activity. This is what we have in the reference implementation in OSP. You can pass it to other activities. So for instance, let's say that you want to show the next maneuver on the passenger display or in some other display in the car. You can just send it on a broadcast and use broadcast receiver to pass this information around. You can also re-encode it and send it to a different unit outside of Android. So for instance, if you want to show this on a rear mirror, or if you want to show it on a heads-up display, you can do so by taking the pieces of this information that you want and re-encode it and pass it through the network. Couple of things to notice in the case of handling images, because the applications are going to be sending these updates very frequently. They are not going to send the bitmaps directly on the object. They're going to just pass. They're going to send URIs to those objects, and in order to actually obtain the bitmap, you're going to use the getContentURI method on the image reference you're going to get. You need to pass the requested size. So the navigation applications are going to use this information to decide what is the best size and asset to pass back. So you take the URI that you receive on the navigation state object, you pass it to getContentURI with the requested size. You're going to get a complete updated URI that you can pass to the second method, the getBitmap on instrument cluster rendering service. We recommend that you don't try to fetch the URI directly. There's some work that needs to be done because of the inter-user communication. Like in this case, the cluster is in user 0. The bitmaps are actually provided by an app that might be running on a different user. So we have taken care of that on this getBitmap method. This method is expensive, so we highly recommend to cache any images that you receive from these apps. The URI that you're going to use is unique to that image, so you can use that URI as a cache key safely. And definitely you need to do this fetching on a secondary thread so you don't block any other processes. The other thing I wanted to talk is about rich text. This is what we use to show or to communicate navigation cues, like the example that I have on the screen. Each of the elements in this sequence is a rich text element that can be an image or a text. If the display where you want to show this information doesn't support image rendering, then there's a second method that is called getText that gives you a full text representation of the same information. This is because it might not be a one-to-one mapping between images and text. In order to test all these, the kitchen sink application has a section where you can test focus, request, and release. It has an automatic playback of pre-recorded navigation events. You can modify these events. This is basically just a JSON file where you can add or modify the events that we are sending. And this is a good way to check that your implementation of the navigation state API is rendering the proper information. So that's basically it. This is we have reviewed all the elements here. Please check the reference implementation on packages apps car cluster. And this is all I have for you. Thank you very much.